Hello everyone and welcome back to the latest instalment of the Australian Geometric PDE seminar series. Today it's my pleasure to introduce to you Hunter Stufflebeam, who's currently a grad student at the University of Pennsylvania. He's currently working under the direction of Davi Maximo. Hunter, would you mind sharing your slides?
Yep.
So I can remind myself what the title of your talk is.
Right, yeah. Probably good to have that up. There you go.
Excellent. So the talk is going to be the stability for convex two disks and a theorem of Toponogov. Thank you very much, Hunter. Take it away.
All right, yeah. Thank you very much for having me. This is my first real result, my first real seminar talk of sorts. So thank you very much for being here. I'm excited to share this with you. So yeah, thanks to Tim and all of you for coming. Thanks also to my advisor, Davi, of course, and I should thank the Fields Institute because a lot of the endgame stuff here was sort of figured out and written up there last month at their scalar curvature workshop. Lots of nice people, nice working conditions. So yeah, that was great. So yeah, let me tell you about a stability theorem for convex two disks. So the outline here, I'll start by telling you sort of the motivation for this. The motivation is an old theorem of Toponogov. And a doomed conjecture I had about it. And so this doomed conjecture, well, it's doomed. So then the next part I want to tell you, like, what could we salvage from this? What could we try to prove, like a next best result to hope for? And then the last part, I'll tell you about what I was actually able to prove. So the motivating theorem here is this theorem from 1959 due to Toponogov. A theorem about closed surfaces. Why is my thing not working? That's weird. I don't have a pointer. Can you see if I do this?
Yes, I saw that.
Okay, my laser pointer is not working, so I'm going to use this to point to things. So if you have a closed surface with Gaussian curvature bigger than or equal to 1, Toponogov's theorem says that any simple closed geodesic in M has length bounded above by 2 pi. And there's an associated rigidity statement here, which says that equality holds. Namely, you have this manifold can have a geodesic of length 2 pi, a simple closed geodesic of length 2 pi, if and only if that manifold is isometric to the round sphere. So a natural question you could ask is this a stable theorem? So if you have such a closed surface and a simple closed geodesic on it that has really big length, so length close to 2 pi, you could ask if this M2G is somehow close to being a round sphere. And you get to kind of decide what closeness means here. In my case, I'm going to say closeness means Gromov-Hausdorff close. And the answer to that is nope. And it's sad. So the counterexample, at least for close meaning Gromov-Hausdorff close, is a football orbifold. So just recall, if you take your S2 here and you mod out by an action of ZK, that's like you're taking this beach ball and you're identifying the sides on this red loon here. You're going to get this little thing called a football orbifold. It's a nice manifold away from these orbifold points at the north and south poles. It's got constant curvature 1. And every meridian, so every one of these curves here, is a simple closed curve of length 2 pi. And it's geodesic away from these orbifold points where the thing's just not smooth. And the kicker here is that this orbifold's Gromov-Hausdorff far from being a round sphere. And the technical point is that it's not a true counterexample. It's not really smooth because of these orbifold points. But it turns out in this paper by Bing Wang and Jinrei Zhao, they were able to take these orbifolds and smooth them out by gluing in a little spherical cap and smoothing in a kind of a complicated way. But it turns out if you look through their construction carefully, you can see that this process doesn't damage the diameter too much, and it preserves the lower curvature bound. So basically, yeah, you can smooth this orbifold out into a true bona fide smooth counterexample to stability in Toponogov's theorem. So yeah, there's no hope of proving stability in Toponogov's theorem because of things like this. But what could we try to study instead now? So what's the next best thing you could say? Well, okay, there are a couple next best things maybe, but I claim it's interesting to actually look at disks. So my goal here is to study two-dimensional disks with the same Gaussian curvature condition. And now since we have boundary, we want to add in a geodesic boundary curvature condition. And so I'm going to ask for the boundary to be strictly convex. And the motivation for this comes from the proof of Toponogov's theorem. So I know of two proofs of this. The original due to Toponogov back in the 50s, which uses Alexandrov space techniques. And then there's a modern PDE proof of this due to Fenboheng and Xiaodong Wang from about 2009. And in both of these proofs, what you do is you take this manifold and you cut it open along the geodesic. So you got your long simple cos geodesic and you cut along it and you get two disks. And then what you do is you formulate an inequality and a rigidity theorem for disks. So this is what Heng and Wang proved. If you have a compact surface with boundary, the Gaussian curvature condition and the convexity condition, then the length of the boundary is bounded by this number here. With equality, if and only if that disk is isometric to a geodesic disk of radius arc cotangent C in the round sphere. And so you can see that if you ask for geodesic boundary, then you can prove Toponogov's original theorem with a C equal to 0 there. Okay, so if you're trying to prove stability in Toponogov's theorem, it's natural to try to start from this proof and try to prove a stability theorem for disks, perhaps, which is what I was trying to do. And of course, you can't do this when the lower bound is equal to 0, but we can do it when you ask for a strictly positive lower bound on the geodesic curvature. So the theorem I worked on for the last few months is the following: fix a C bigger than 0. Oops, that's an eraser. I don't want to actually erase stuff. So fix a C bigger than 0 and a delta bigger than 0. Then the theorem says that there's an epsilon, so that if I have this compact surface with Gaussian curvature bigger than or equal to 1 and C convex boundary where C is positive, and if I ask for the length of that boundary to be big relative to the maximal upper bound, then this disk has to be close in the Gromov-Hausdorff sense to this model disk in the sphere, this model disk of this geodesic disk of radius arc cotangent as C. All right, so this is what I'm going to try to prove, and I'm sort of looking at this as like a next best thing you could study after trying to prove this doomed stability in Toponogov's theorem. So, okay, I should ask: are there any questions about like what I'm trying to do or why? Okay, I mean, interrupt me at any time, of course. So, to get started, I want to recap the proof of the disk theorem from Heng and Wang's paper, because it sets the stage in notation and some of the ideas. So here I've just reproduced it for your convenience here. The first thing to note is that by Gauss-Bonnet uniformization, if I take this disk, it's going to be isometric to the unit ball with this metric conformal to the Euclidean metric. So uniformization is going to hand me this conformal factor, whoops, and give me an isometric realization of this manifold, like so. Now, the curvature conditions are going to translate into this PDE here. So this is recording the Gaussian curvature on the interior of the ball, and this is recording the geodesic curvature on the boundary here. Really wish I had that laser pointer. It's too bad. So the good idea here is that using this technique from PDEs, the sub-super solution method, given this disk here, we can produce a constant curvature disk to compare it to, with the property that both of these disks, our original disk and the constant curvature comparison disk, have isometric boundary. And this is just done by messing around with the conformal factor. So what this method produces for us is a new disk with this new conformal factor. So the conformal factor satisfies this PDE. That says it has constant curvature 1. It's going to be equal to U along the boundary. So that's telling you it has isometric boundaries. And then as a consequence of the construction, we see that this new constant curvature comparison disk is also C convex, and this other convenient thing, which is that U dominates V on the interior. So we started with our mystery manifolds, which I've just erased. And from these mystery manifolds, we can produce constant curvature things to compare them to. Okay, so this is just recapping what I had on the last page here in PDE form. So what we can do is, because this disk has constant curvature 1, we can isometrically realize it as some domain in the standard 2 sphere. And by doing so, we can really directly estimate its boundary length just from simple geometry. So picture might look like that. We know that because of this lower curvature bound here, this domain, this convex domain, this isometric realization of this constant curvature comparison disk, it's the smallest geodesic disk in the sphere which contains it is gonna be the model disk that we want as sort of our extremizer in the problem. All right, and then why is this good? Well, we know that the length of our original manifold is just equal to that from this realization here. By the construction, these are the same. These have the same boundary length. And by this isometric realization as a domain in the sphere, the length of this is equal to the length of the boundary of this purple domain. But the kicker is that by convexity, we can estimate that in terms of the boundary length of that geodesic disk. And we know what that is. It's just 2 pi over square root of 1 plus c. So that proves the inequality, which is pretty nifty. And I think what's even more nifty is how easily this proof handles the equality case. So if we have equality, so if the domain of our, or if the boundary of our original domain is as big as it could possibly be, so it equals this upper bound, then that actually forces this constant curvature comparison disk to be the entire geodesic disk that was acting as like an outball for it. So that's what this is telling us. This maximal length being realized tells us that the constant curvature comparison disk has to be this geometric or this geodesic disk. And so that tells us that the boundary curvature of the constant curvature comparison disk is exactly C. So this is what the PDE conditions update to now that we know that we have this equality here. Whoops. And so now if we look back on how did our conditions compare on the boundary for U and V? Well, okay, so this is the curvature, boundary curvature constantly equal to C condition that we just discussed. The super solution method construction gives us this inequality here between the normal derivative V and the normal derivative U. Because remember, V is a solution of the PDE, U is a super solution, and there's this ordering. This inequality is the original convexity condition on U. And then this is, again, from the construction where U is equal to V on the boundary. But basically the point here is that we have a sandwich happening. So knowing that the length is maximal up here also tells us that our original disks have constant boundary curvature. So now all we have to do is we set W to be the difference of the conformal factors. And well, what does that satisfy? Well, it's a super solution of the Laplace equation. It's got 0 Neumann and Dirichlet conditions. So W's got to be 0. And I'm sorry, I made a little typo there. This should be a W. That should be a W. And by virtue of this, U has got to be identically equal to V. So the original manifold has to be this constant curvature disk. So equality falls out pretty easily. Whoops. Okay, so we just went over the proof of that theorem due to Heng and Wang. And so this is now what I want to tell you about. This is the stability version of this result. So again, I'm just trying to take a disk like this where the boundary length is really big, and I'm trying to show that it's got to be Gromov-Hausdorff close to this model disk. And remember, I have to impose this condition that the lower bound is strictly positive. That's important. Okay. So the proof is by contradiction. Supposing that we have some delta knot so that we can find a sequence of these manifolds that have Gaussian curvature bigger than or equal to 1, geodesic curvature of the boundary bigger than or equal to C bigger than 0. And I want the lengths of the boundary to converge up to the maximal possible length. Okay, and then for the sake of contradiction, I'm going to assume that this sequence always stays far away from the geodesic model space. Okay, so all that translates into the following. We get a sequence of disks. So using the Gauss-Bonnet and uniformization, we can represent our sequence that we've come up with for contradiction as a sequence of, we're really going to look at the sequence of conformal factors here. They satisfy some PDE conditions. And then for each one of these, we'll also construct the constant curvature comparison disk in the same way as we did in Hang-Wang's proof. And then they satisfy some PDE conditions. And we know that the lengths are converging up to their maximal possible value. So the goal is to produce a subsequence. So for contradiction, our goal is to produce a subsequence of these disks, which does converge in Gromov-Hausdorff to this model disk. So we need to take a limit of these metrics. And the first step here is to understand what's happening with these constant curvature disks that we're comparing to. And this gets a little dicey because there's a gauge invariance going on. So it's, sorry, is there a question? Sorry. Okay, so what does gauge invariance mean here? So if we have any Mobius transformation of the unit ball, this Mobius transformation is going to be an isometry between these two manifolds here. So our original constant curvature comparison disk and this new disk with this new funky conformal factor that has this formula here. Sorry, that copy thing is blocking the writing. So both of these conformal factors represent the same exact geometric object because they just give an isometry. But the point is that they could be very, very different analytically, because if I try to take, some Sobolev norm or something of this conformal factor, who knows what's going on? I mean, this is a big group, so I'm going to have a big loss of compactness. It's a big mess. So this geometric information is still the same, but it's kind of unclear what the right way to look at it analytically is a priori, because any one of these representations is just as good from the geometric standpoint. So let's see, so a quick definition, just to get it out of the way. For C bigger than or equal to 0, I want to define the model spaces that I want to converge to. So we're going to let RC be this thing here. This is a radius, and rho C be this function here. That's a conformal factor. And the point is just that the model disk of radiant arc cotangent C that we want to converge to is isometric to either of these things. So either the unit ball with this conformal factor, or it's this slightly smaller ball with the round metric. And all this is just coming from stereographic projection. So you'll see this notation flying around. That's why I want to introduce it right now. Okay, so back to the gauge issue. If we want to take a limit of the sequence of these constant curvature comparison disks, the proposition is that we can find Mobius transformations phi k, so that if I gauge correct them like this, so if I find a different sequence of conformal factors representing the same geometric objects, the claim is that I can do this in the right way so that these now converge to the conformal factor of the model disk that I want, and they're going to converge in CM loc of B1, where M is just any integer bigger than or equal to 0. So reparametrizing in this way gives us an analytically nice way to represent our original manifolds and the things we're comparing them to. And so the gauge fixing process is going to be, well, we take the UK and the VK, and we're just going to replace them with these factors that correct it. And we're just going to assume that we've done this a priori in the rest of the argument. I'll go into more detail about this. I just want to give you an overview right now. But so to fix the gauge, to take the limits and make the estimates we want, we replace these original conformal factors that were just handed to us from uniformization, these things that we don't really have a good grasp on. We're going to replace them with quantities that are just as good geometrically, but much nicer analytically. Okay, so we'll continue to, so the result of this first step is we'll be able to get this convergence, this smooth local convergence on these comparison disks. And yeah, just to keep the notation simple, I'll not put the phi k's and everything. But so that's the result of that first step. We can correct the gauge and get nice local smooth different hierarchies of smooth convergence. Okay, step 2 is to understand the relationship between the original conformal factors, the UKs, and the constant curvature comparison factors, the VKs. And this is largely just a sequence of standard PDE techniques, so I won't say too much about it. But basically what we do is we write WK is equal to UK minus VK. And the proposition that we prove is that, well, if you take any scalar bigger than 1, and any p between 1 and 2 like that, then we have this Sobolev convergence here. That's the punchline of this second step. All right, so that's the result. And step 3 is we're going to pair this knowledge together, identify the limit, and then in step 4, we'll identify the limit of the original sequence. And so the idea here is to write the difference between our given conformal factors and the model conformal factors. And then we're going to expand it out like this, where we have the constant curvature guys here, and then this difference conformal factor here. And using the results from the first 2 steps, we can get this sort of convergence here, not that sort of convergence. W1P loc on B1 for P between 1 and 2. All right, so once we have that information, what does that imply? Well, first off, we can show that that implies that if you look at a slightly smaller disk here and you close it up, then these manifolds converge in the Gromov-Lipschitz sense, like their underlying metric spaces converge in the Gromov-Lipschitz sense to the correct things. The heuristic, I mean, okay, so we really want to show that the Gromov-Hausdorff limit of the full disks is this spherical cap, but it's much easier to work locally first because the limits are easier to identify. And then afterwards, what we do is we use some other notions of convergence to sort of union them together and identify the whole limit with R equal 1. So that's why, so we're gonna restrict attention to a smaller ball first where we have good estimates. Because remember, we just have W1P loc information here. So that's why we gotta restrict down to this ball, this smaller ball. Okay, so in the next step, we show that the whole ball converges in the Sormani-Wenger intrinsic flat sense to the correct limit. This is in the sense of integral current spaces, but don't worry too much about what that is. All these things are manifolds, so nothing's that intense here. And then the last step is showing that the whole sequence converges in the Gromov-Hausdorff sense. And this going from here to here amounts to showing that in our situation, Sormani-Wenger intrinsic flat is the same thing as Gromov-Hausdorff. All right. Okay, so that's the outline. Are there any questions about anything so far? Okay, cool. And yeah, again, please interrupt me whenever. So let me tell you a little bit about this gauge fixing thing first. So remember, our goal is we've got these constant curvature disks to compare our original manifolds to. And we want to take a limit of these. So our goal is this line up here. The first thing we'll do is we'll make an initial choice of gauge. We'll make an initial choice in representing these things. So we can isometrically realize them as smooth convex domains in the 2-sphere. And we're going to do it such that each one of them contains the south pole. And each one of them is contained in this model disk, right? This geodesic disk of radius arc cotangent of C centered at the south pole in the round metric. Okay, and sort of the key observation that I'll say more about on the next page too, is that these domains also have large inballs. By virtue of their boundary lengths being big and being convex, they have to have big inballs. And specifically, they have an inball with this radius. What's important here, I use this notation phi k or psi of epsilon k to mean that psi of epsilon k goes to 0 as k goes to infinity. I think this is traditional notation due to Cheeger probably. But point being, these inballs converge up to the outball as k goes off to infinity. So these domains, these purple domains get squeezed up to the ball in a nice way, in a nice organized way. Okay, so I claim that we can do this. The reason is because of this, or is explained, I guess, by this theorem of Konstantin Drach from 2018. If you let omega be a smooth convex domain in S2 with boundary length L and strictly convex boundary, then you get a pretty explicit estimate for the in radius here, like this. And so if we plug in the lengths of our domains with all this data, then we see that the in radius of our domains looks like this, which is converging up to the radius of the outball. And then because I can't necessarily center this ball at the South Pole, I can find a slightly smaller one. Whoops. It's also centered at the South Pole, but this green ball also converges outward. So the point is that these isometric realizations of the constant curvature comparison disks have a fixed out ball, and they have an in ball that converges and pushes the domain up to the out ball. So this green ball expands outwards as k goes to infinity and pushes the purple domain out to the ball. Okay, so we'll do one last little thing here, and then we'll be able to start saying things about convergence. If we then use stereographic projection to put all this into the plane, whoops, I see there's a picture on the next page to explain this. So we have our domains here, and under stereographic projection from the North Pole, they're going to be these disks with a round metric are going to be isometric to these sorts of disks here, where this is a smooth convex domain in R2, contains 0. It's nestled between some ball and some other ball, and then these inner radii expand outwards. That's just the in balls getting bigger. Okay, so let me just show you a picture of what this looks like. These are our constant curvature comparison disks down in the southern hemisphere containing the South Pole. Under stereographic projection, they go to these purple planar disks. And then the in ball is this little green guy here, and that converges outwards to this this out ball here of radius RC. Okay. Hopefully that's not too quick. It's a lot of different disks representing the same thing. But the upshot to this is that okay, so this our original constant curvature comparison disk, which was made out of kind of black magic, I guess, it's just handed to us from PDE theory, is isometric to this thing that like we can kind of get our hands on a bit. It's just you got the round metric on some smooth convex domain in the plane with a big in ball and a fixed out ball, and there's an isometry relating them. Should put a K in there like that. So if we unwrap what this isometry is doing, well, this isometry is a diffeomorphism of the ball in this convex domain, and it pulls back the metric like that. Okay, so this last condition tells us actually, okay, so FK is conformal. If we look at everything in terms of complex analysis, it's a biholomorphism between B1 and this convex domain here. And the key point is that, so we're trying to take a limit of these conformal factors effectively to talk about smooth convergence. Well, we have a way of relating this mystery conformal factor to the round metric. And it's via this map F. And the point is that we can understand and take limits of maps like this. So we have very nice maps. They're conformal diffeomorphisms, and they relate our constant curvature comparison factors to potential limits, the round metric, in this funky way. Oh yeah, and then the prime here means complex differentiation. So our problem reduces effectively to studying sequences of these conformal maps in the plane, where their images are they're nestled inside of some fixed ball. They have in balls that converge out to the out ball, and then we have this formula here relating the conformal factors. And of course, like I said, the question is now, do they converge? How do they converge? How can we use this? Okay, so the proposition is that we can find Mobius transformations so that if you pull back these isomorphisms or these diffeomorphisms, these conformal maps with these Mobius transformations, then this new reparametrized sequence converges to RC. Remember, that's just this radius here times the identity map. So in particular, what this will show, I'll explain why in a sec, is that if you gauge correct the conformal factors, by making this like changing the conformal factor to that object there, then they converge like I claim they do to the round metric, or the spherical cat metric, I should say. Okay, so the proof of this goes like so. First choose some Mobius transformations to normalize the original sequence of conformal maps. There's your standard complex analysis normalization trick. And so now we have a sequence of these normalized maps. They're biholomorphic. They go between simply connected domains. And this original gauge fixing we did where we chose these domains ensures that the domains converge to their outballs in the sense of what's called kernel convergence. And that's a notion due to Kara Theodori that I kind of don't want to write out because it's just like kind of a mouthful. But the point is that our initial choice of gauge makes it very, very easy to check this condition. And why on earth would you care about kernel convergence? Is because there's a famous theorem, the Kara Theodori kernel theorem, which says that if you have a sequence of simply connected domains containing 0, ours do, and some bijective conformal maps, which are normalized like we do up here, then the conclusion is these maps will have a limit map in C0 loc if and only if the image domains converge in the kernel sense. And in the event that the kernel is non-trivial, in our case, the kernel is this ball here, then the domain is simply connected, whatever, we knew that. But what we learn is that the limit map that we converge to is also a conformal diffeomorphism. So these maps will converge to a conformal diffeomorphism between B1 and the ball of radius RC after we've reparameterized them to normalize them. Okay, so that just means that it's some scaling of a Mobius transformation. So now if we pull back by this Mobius transformation, then we're going to produce these gauge correcting Mobius transformations I originally advertised. So if we set f hat k equal to this normalized version pulled back by the limit here, and then I just call this junk here phi k, we have that these new conformal diffeomorphisms between the unit ball and these domains dk, they'll converge in C0 loc to RC times the identity map. And by Cauchy integral formula, we can upgrade that to CM loc, if we just go a little bit smaller. And so what's the point? Well, let's pull everything back by f hat k now. So here's our original, so here's our original constant curvature comparison disk. That's the same as this dk with the round metric under this, under our original isometry fk here. So on the one hand, if I pull back by this Mobius transformation, I get this formula here. And this is because of conformality. And this right here is just this f hat k I just constructed, and this takes me to this disk like that. So all these equalities just mean isomorphisms. I'm starting to accidentally delete stuff now. And again, this formula here just means this sort of thing. So the whole point is that we were able to correct these maps. Okay, so what we have is that we have this gauge corrected conformal factor right here is equal to this object over here. And we know that this thing right here is converging nicely. And so if we unwrap what that says, well, it says that these gauge corrected conformal factors converge to the round metric composed with RC times the identity plus logarithm of RC. Well, you can check that that's just exactly rho C. So we have that convergence now. Okay, so now we can fix the gauge once and for all. So recall that because we had Mobius transformations like this, because of the conformality, this thing is isometric to this thing is isometric to this thing. So remember, this is our original sequence of disks that we were looking at studying. And these are the constant curvature versions that we were comparing to. So these are the same geometric objects. So what we can do is we can just replace these conformal factors with these conformal factors. And for instance, all of the PDE data a posteriori is all satisfied because they represent the same, these are geometric PDEs, so they mean the same thing. So our gauge correcting procedure is we're going to take these conformal factors, replace them with the corrected ones, and then for WK, we'll replace that with the difference of these. All right, so assuming we've done that already, now we have good convergence on the constant curvature comparison disks. So now let's go on to step 2. I should ask, any questions about that? Okay, So step 2 now is to relate the constant curvature comparison factors to the original ones. So we look at WK as UK minus VK. And just using standard PDE techniques, we can get enough information on convergence of these to be in business. So the main lemma here is just this list of facts. It's a super solution, it's non-negative, so on and so forth. The interesting one, I think, is this last one here. So that last conclusion is what comes from the geometry of the situation. So maybe let me say one word about that real quick. Is think about the integral of the normal derivative of WK. So remember, this notation here means that this is going to 0 as k goes to infinity. So if I write out what the normal derivative of WK is, this is just the definition of W. So I can write the normal derivative of WK as this difference of like curvature measure densities for the boundary. And if I integrate this now, I can use Gauss-Bonnet to estimate the last difference. And when you use Gauss-Bonnet, you get these area terms. And so you want to say something about areas. So again, what happens is this theorem of Drach with this in-radius estimate comes to help you, because it tells you that you have volume convergence for these constant curvature conformal factors that you're comparing to. That allows you to control the area terms in Gauss-Bonnet, and that allows you to control the integral up here, and thus the integral over here. So this conclusion is really coming from the geometry, which I think is kind of interesting. Everything else just comes from the PDEs. So, okay, once we have that, we can get L1 convergence of the Laplacians to 0, and we can compare, and we can pair that with this sort of Moser-Trutinger-esque inequality due to Brézian-Merle. To get, first we get a bound that looks like this. So e to the p WK is bounded for all p between 1 and infinity in the limit. You can pair that, or you can get using like Green's function estimates, you can get a gradient estimate on WK. You can pair these things together to get a gradient estimate on e to the lambda WK now. And then finally, you put all that together with Sobolev embedding trace inequalities, things like this, Poincare inequalities, what have you. And you can prove the theorem I claimed a little while ago. So if you have a p between 1 and 2 and a lambda bigger than or equal to 1, then e to the lambda WK converges to 1 and W1p of the ball. Sk goes to infinity. So just standard PDE techniques there, nothing too special. Okay, so step 3, we'd make this difference. Like I said earlier, you take the disks or the conformal factors you've been given. I put a lambda in here because sometimes I have to use a lambda equal 1, sometimes I use a lambda equal 2 to do different things, whether I'm talking about like areas or lengths. So it's just convenient to have convergence for all these lambdas here. But anyways, you want to get convergence of these conformal factors. So you write it out like this in terms of the constant curvature comparison disks, this difference of conformal factors, so on and so forth. And we know from the prior 2 parts that this part converges nicely, this part's bounded, this part converges nicely, this thing is just smooth and bounded. So by Holder-Sobolev inequality, the last 2 steps tell us that we get W1p low convergence of this whole thing for any p between 1 and 2. Okay, so what can we do with this? That was a pretty quick step. So step 4 is identifying the limits now. So our first proposition is that we can use this W1p low convergence to say something about distance functions. So the first proposition is that if you take the distance functions of our original manifolds, they're going to converge in C0 loc to the distance function deriving from this spherical cap metric. So this is the encoding of the local Gromov-Lipschitz convergence. So the proof of this is, the first step is produce a limit, just some continuous limit. And this is done with Maury-Sobolev, the Maury-Sobolev inequality and compact and Bengzel Holder spaces, again, pretty standard stuff. And the key estimate is that if you take the gradient of one of these distance functions, this is just the conformal factor here. We have W1P loc control. So if we restrict to like this this ball of radius r for r less than 1, we have a uniform bound on the P norms of the gradients of these distance functions. So then we can, use Morey-Sobolev and compactness of Holder spaces to produce some continuous limit for these distance functions. We know it'll satisfy the triangle inequality. It'll be symmetric just because they're a uniform limit. But a priori, they're just semi-metrics or semi-distance functions. They might collapse. So you might be worried about that, but we can show directly actually that the limit has to be the distance function deriving from the spherical cap metric. So this happens in two parts. You show inequalities in both directions. First one is Sobolev trace theorem, and the second one is Bishop-Gromov, basically. So in the first step, for this inequality, this direction of inequality, just take 2 points. Whoops. Take 2 points in the ball, enclose them in some region like that, and then take a round metric geodesic from X to Y. By convexity, that'll live inside of this set. And then, so what we know is that we have W1P convergence on this smaller closed ball for here. And then by the trace theorem, we can get LP convergence along that geodesic. And then this just allows us to directly compare the lengths of lengths of various curves. So that's all fine and good. We get this one direction of inequality for our distance function. The other one is the other direction of inequality is a proof by contradiction. So if we suppose, for the sake of contradiction, there are some pair of points, we can enclose them in some smaller compact ball. If we suppose that the d infinity distance between them was strictly smaller than what we think it should be, then we can come up with a contradiction. So think of X as a base point here and look at balls centered at X. So because this, okay, so Y is going to be in the ball of radius R in the infinity metric. See, here I've drawn the R level set of that function, and Y is going to lie inside of that. But Y does live on the boundary of the ball of radius R in the round distance functions metric, like that. So by continuity of this limit function here, we know that there will be this little green open set of points floating out here, which lies outside of the yellow ball. So if we take the round volume of these sets, we have a strict inequality due to the presence of this little green open set here. Okay, so we can contradict that because the UK are converging uniformly on BR. So, okay, if we shrink in a little bit like this, so if we take a little scale and we shrink in a little bit and then we localize, this is just technical, but basically because these distance functions are converging locally, these smaller balls are eventually going to be contained in the balls of radius R about X with respect to the distance functions in the sequence. So these balls in here will be contained inside of this ball. Okay. So if I take the round volume of that inequality there, and then I apply Bishop-Gromov here, there should be a UK here, like that. And then if I send R to 1 and then eta to 0, I take a union of these things over a sequence as R goes to 1 and eta goes to 0. Use the fact that that's a Rodon measure, if you like. I'll get an inequality which goes the other direction here. So using the curvature, I can contradict this inequality here. Kind of interesting. So we get inequalities going both ways. So we conclude that the distance function that we limit to is indeed this function that the distance functions converge to has to be a bona fide distance function. And more than that, it's the distance function deriving from the round metric, which is what we wanted all along. And so you can rephrase this as saying that if you restrict to this smaller ball BR, you get Gromov-Lipschitz convergence of these disks to these smaller model disks. Okay, and then the last two parts here are showing that we have this intrinsic flat convergence, and we have agreement of the switch between the intrinsic flat limits and the Gromov-Hausdorff limits. Okay, so let me tell you a quick thing about SWIFT and GH convergence, just a little bit. Recall, I guess the Gromov-Hausdorff distance is a distance between compact metric spaces. What you do is you take your two favorite compact metric spaces, you put them in your favorite ambient metric space, compact metric space with distance preserving maps. And then you measure their Hausdorff distances inside of this space. And then you infimize over all the different ways you could do that. So you find the most efficient way to put these two metric spaces inside of something else to compare them to. And that gives you your Gromov-Hausdorff distance. So intrinsic flat distance is sort of the same idea, but instead of looking at the Hausdorff distance of the thing, or Hausdorff distance in the thing that you're embedding into, you look at the Federer-Fleming flat distance of the thing you're embedding into. So it's a distance on currents, on oriented things. So it looks like this. If you have oriented Riemannian manifolds and you embed them in a distance preserving way into a common complete metric space Z. So again, you got our two guys here oriented, you put them inside of this metric space, distance preserving way like that. You then want to treat these as currents in the sense of Ambrosio-Pirkheim. And if you don't know what this is, don't worry too much about it. I'm lying a little bit here, but if you think about the Euclidean case, if you like, basically, if I realize these things as currents, I'm trying to capture how they act as functionals on differential forms through integration. In metric spaces, of course, you don't have differential forms, so you need to do something a little different here. But think about it like this: like if you have a differential form on this ambient metric space, the way that your this manifold acts on those differential forms is just by integration over the manifold in a continuous way. So it's a little imprecise in the full generality of metric spaces, but actually in what I'll use here, everything will be a Riemannian manifold. So this is actually all true and correct. But in general, you need to do something a little different. But once we do this, so once we've embedded these things as currents, we can measure their Federer-Fleming flat distance, which just looks like this. And what it means is, so you take your things have an orientation, and so you look at their difference as oriented things acting on differential forms, and you ask for all the different ways you can represent this as currents of the form A plus boundary beta. So what this formula means here is that if you're given a differential form on the ambient space, then integrating everything obeys this rule here. So you have this A plus boundary B here, and then you have this M minus N thing going on here. And then what you do is every time you find a representation like this, you add the mass of A. So think of that as like an M-dimensional volume of A, and then you add to that the M plus 1-dimensional volume of B. So the picture you should have in mind really is this sort of thing here, where you have your one metric space here, and what you do is you close, and then you have your other metric space or your other current here, and A works to close up the boundary. So if these guys have boundary, A works to close up the boundary, and then B fills it in like this. So that's this A plus boundary B. And then the way to estimate the flat distance is then like this. This is what we'll use in what we do. Basically it's a thing about filling volumes. So you take the volume of the thing in here plus how much you had to spend to close up the boundary. So really things are close in the intrinsic flat sense if their filling volumes are small, is sort of the motto to keep in mind. And this gives a really nice way of estimating this distance. You don't really need to compute. It's like Gromov-Hausdorff distance. You don't really need to compute it a lot explicitly, but you want to try to bound it a lot of times. And it's often you can kind of create these things and estimate them directly like this in a very hands-on way, which is what we'll do. So, right, and then, okay, so once we've done that, we've computed the flat distance, and we do the same thing that we did in the Gromov-Hausdorff definition, where we just then infimize over all the different ways we could do this. We infimize over all the different Z that we could have embedded into with all the different distance versioning maps we could have used to embed. And the infimum of all those things gives us the intrinsic flat distance between M and N. Okay, so some quick facts are that uniform convergence of distance functions on a compact space give you Gromov-Lipschitz convergence. And then Gromov-Lipschitz convergence implies both intrinsic flat and Swift convergence. That's a theorem of Gromov and Sormani-Wenger independently. Gromov was for this and Sormani-Wenger was for that, naturally. I should also mention that there are two compactness theorems that we don't really need. It's just nice to note them. But so there are compactness theorems for Gromov-Hausdorff. There are compactness theorems for intrinsic flat. And in particular, our sequence of manifolds satisfies both of these. So we know that they're going to Gromov-Hausdorff converge to something, and we know that they'll intrinsic flat converge to something. The trick is figuring out what those things are. And the local Gromov-Lipschitz convergence that we just proved will help us show what these somethings are. They're exactly the model disk that we want. And to that, we add one other last tool, which is this theorem of Perales from 2021, which says the following. It's a theorem about when intrinsic flat agrees with Gromov-Hausdorff for manifolds with boundary. There are other theorems for closed manifolds. Most of the theorems out there are for closed manifolds, and Raquel Perales has done a lot of work to extend these things to manifolds with boundary. And so this is a little bit of a mouthful, but basically what we have is we have a sequence of compact oriented two manifolds. This is adapted from her theorem to my situation, kind of. So this is not exactly how it appears in her papers, but let MKGK be a sequence of these guys with boundaries so that you have a curvature condition here, non-negative curvature. You have uniform area and length bounds, area bounds on the manifolds, length bounds on the boundary. And then there's a diameter bound on these inner regions. So what I mean by inner region is I just take my manifold with boundary, and then I look at the region formed by all points that are delta I away from the boundary, where delta I is a sequence going to 0. And I want there to be a bound for each delta I independent of K for these regions. Here, this metric is the induced intrinsic metric to this subspace. Okay, there's also a non-collapsing condition, an area non-collapsing condition. And then we need some sort of boundary control. So there exists a compact metric space to which the boundaries limit in Gromov-Hausdorff. Okay, so with all of these ingredients in the pot, what we can produce is a Gromov-Hausdorff limit and a Swift limit, which is isometrically sitting inside of the Gromov-Hausdorff limit. And crucially, if we can prove that the limit of the boundaries lies inside of the Swift limit, then the two limits have to agree. Okay, so checking these conditions with our original sequence of disks isn't too bad, because A, B, and C, the length, area, curvature bound, are immediate from our assumptions. This condition on the inner regions here is satisfied with di equal to pi by convexity. So by convexity, the induced intrinsic metric is just going to be the restricted metric, and the original metrics were all bounded. So that condition is satisfied. Non-collapsing is satisfied because of the local Gromov-Lipschitz convergence, because we have good volume convergence there. So that condition, so the non-collapsing condition is satisfied. And lastly, these two final conditions hold because if you remember, the boundary of our original sequence is isometric to this boundary of domains in the sphere. The boundary, remember, the boundaries of our original sequence are isometric to the boundaries of the constant curvature comparison disks. And those are isometric to these domains in the sphere. But it's really easy to see that these domains in the sphere, Hausdorff converge to the model disk. So we have Gromov-Hausdorff convergence of the boundaries to the boundary of the model disk. And we're about to show that the model disk right there is the Swift limit. So that closes the loop, and this theorem applies, shows us that the Swift limit is exactly the Gromov-Hausdorff limit. And so the last step is just to prove that this full sequence of disks converges to the, in the Swift sense, to this spherical cap, this geodesic disk of radius r cotangent at C. So we fix a radius less than 1, and we use a triangle inequality to estimate the intrinsic flat distance. We jump from the full ball to the ball of radius r, and then we jump from the ball of radius r to the ball of radius r, and then from the ball of radius r on the model disk back to the full model disk, like that. Okay, so the second term here goes to 0 because Gromov-Lipschitz convergence implies intrinsic flat convergence by that result of Sormani and Wenger that I mentioned earlier. In terms 2 and 3 are estimated in the same way by directly constructing this space to embed into. So in the picture here, this is the full disk right here, and this is the disk of radius r. And what I'm going to do is I'm going to put them, Z is going to be this whole space here. So I'm going to let BK, like this sort of filling volume, this filling manifold, be the original manifold times this interval where the epsilon k's are going to 0. And I'm just going to give it the product metric, the Riemannian product metric. And then A, the thing that I need to use to close up everything is going to be, well, the sides for sure. So that's this S1 cross the cylinder here. And then I also have to throw in this annulus like that. Okay. So by just constructing this particular embedding space, I can estimate the intrinsic flat distance with the sum of these volumes, the volume of the orange and the volume of the green. And that's more or less pretty simple to do. The only thing that you might be worried about really is the volume of this annulus here, whether or not that goes to 0. But we can estimate that pretty easily. Of course, this is equal to, so if I look at the volume of this annulus, this is equal to, if I took the volume of the whole ball in the UK metric and then subtracted the UK volume of the smaller interior ball of radius r. But by the curvature condition, because the UKs have higher curvature than the VKs, I can upper bound them with the volume of the constant, or the area of the constant curvature comparison disks. And I know that as K goes to infinity, well, the constant curvature comparison disks volume converge to the area of the model disk. And then I know that by Gromov-Lipschitz convergence, this interior ball converges to something, well, what is the something? It's the area of a ball of slightly smaller radius, where I can control like how far the radius is from the model case. And so the point is that this term right here for big enough K is less than or equal to this term that goes to 0 as R goes to 1. Doesn't want to write anymore. There we go. So if I put that together, I can show that, and the same analysis works for term 3, which was the corresponding, the estimate for the annulus on the other, where instead of here I have the rho C term. So it's even easier. If I throw all that together, I get something that looks like this. And since R less than 1 was arbitrary, we're done. The intrinsic flat limit distance goes to 0. So everything converges in the way we want. All right, so I think that's, yeah, we're done. So thank you. Here are some references. Yeah, any questions?
Awesome, let's thank the speaker. Indeed, does anyone have any questions for Hunter?
I had one question, yeah. So it wasn't quite clear to me. There's one place where the lower bound on the curvature of the boundary comes in, which is using the Drach result. Is there other places where you're using that? Or could you replace that? I mean, is that kind of, you could replace that bit of the black box by something different, which gives you an in radius lower bound, for example?
Good question. I only use that in radius lower bound there to do this sort of kernel convergence thing, right? To get a handle on these disks. Yeah. I don't think I'm using it anywhere else. you can use it to get volume convergence, and you might hope that that would tell you some nice things, but I don't know. It's not super clear that
Sure.
gives you
Okay.
nice things.
I mean,
So,
it's tempting to think you could get a version of something, an analog of the Dirac result, if you assumed, for example, boundary curvature greater than or equal to 0, but bounded above. Would that be plausible?
bounded above, yeah, and I think the idea there is like if you have, I mean, so you might take a, there's your sphere. Yeah, I mean, you'd be worried that there'd be some sort of curve that looks like this, I think, right? Where this doesn't have an in radius estimate. It's got close to geodesic boundary, all along here, but right at these tips, it has very large curvature.
Yeah.
So it's like
so
it's trying to fold in on itself. So
that's
trying
right.
to penalize that, yeah, maybe. Yeah, that's quite possible. Also, I think that I'm not sure about this. I haven't said, maybe I shouldn't say this, but I think that this is sort of like the constant curvature comparison disc that you would get for like these footballs. I think, actually, yeah. Yeah, thank you.
Thanks.
Any other comments or questions for Hunter? I suppose I could ask the obvious one. There is a version of Toponogov's theorem for higher dimensions, but I noticed in your proof that well, you're quite heavily reliant on Gauss-Bonnet as well as uniformization. What, if anything, can you say about this problem in higher dimensions?
That's a really good question. Something I'm interested in. Well, let me say, okay, there are a couple of things I could say.
First of all, like, do your counterexamples work in higher dimensions?
Probably, yeah. If you ask in terms of diameter, sure, absolutely. If you ask for a stronger invariant, something like the width, then the answer is no. You actually do get stability for things in terms of width. That's what I actually wanted to mention, is that Davi and Richard Bamler have a result about stability of this inequality for width, like almost maximal width. So if you ask for a stronger invariant, then yeah, you do get that. But with the diameter, no.
So I guess, well, it all comes down to which geometric quantities you're actually trying to study and control here.
Right, and I was honestly quite disappointed that the length of this geodesic wasn't strong enough in 2 dimensions. I thought it was one of those things that was too pretty to fail, and that was a lot of naivete, but such as it is.
There is a conjecture in higher dimensions, which I think is not appropriate for stability, probably, which says that if the section curve is greater than 1 and you have a simple closed residual length 2 pi, it must be a round sphere. So that would be like the analog of Toponogov in dimension 2, which there's some evidence for that that is equal to 2. So kind of the rigid version of Toponogov in dimension 2. Something like that should be true also in high dimensions. Well, then it's very unlikely there's any kind of stability. It's a different kind of question. The dimension's kind of wrong, right? You want something codimensional, one kind of object to get a stability.
Sure.
Right? But that's sort of an interesting question, which is still open. That analog of Toponogov holds in higher dimensions.
Well, I should mention a fun fact, actually. This Toponogov result, or this disk result, is actually Minu's conjecture in dimension 2. That's a fun remark, actually. Like, Minu's conjecture is wrong in general. Like, it's not true, but it is true in dimension 2, and the result is this Toponogov thing. So stability in Minu doesn't hold in dimension 2 is, I guess, what you could call my thing. I guess, I don't know. But yeah. So that's kind of a neat, expensive way of saying all this.
Cool. Well, unless there are any other questions, I think we'll wrap up there. So let's thank our speaker again.
Thanks.
Yeah, and thank you all very much. Yeah, great pleasure.
Nice talk, Hunter.
Yes, it was good
Yeah,
to
well
have
done.
you, Hunter. I'll stop recording now. wait, where is it? There we go.